Hi everyone, I'm Fraser Cain. I'm the publisher of Universe Today. I've been a space and astronomy news journalist for over 20 years. This is the question show. Your questions, my answers. Now, wherever you are across my channel, if a question just pops in your brain, just write it down. I will gather a bunch of those up and I will answer them here. Now, I do this show live every Monday at 5 p.m. Pacific time. So if you want to join the conversation, ask your questions live, get answers, follow on questions, join the conversation, you should definitely come and do that. Now, you're going to see some codes assigned with every single question. It's going to be the name of a planet in the Star Wars universe. No shade on the Star Trek universe. But those codes are your way to vote for what you think was the best question this week. So when you post your comments down below, just put in the code and then go ahead and write anything else or just the code that will let us know who asked the best question, what you thought was the coolest sort of, I guess, question-answer combo. And we'll give a shout out to whoever was the winner next week. All right, let's get into the questions. Daos, what's your take on the proposal to focus on Venus before Mars in terms of crewed human missions, not to the surface obviously, both as a practice run for future Mars trips and scientific data gathering as presented recently at the IAC in Paris? The idea seems to have a lot going for it. I believe NASA's chief economist, Alexander McDonald, is a proponent. Yeah, so this story has been making the rounds for the last couple of days, and this was a presentation that was made at the IAC, the International Astronautical Conference. I mean, this is where Elon Musk originally proposed the idea of the interplanetary transport system that eventually became the BFR, which eventually became Starship. So a lot of really cool announcements happened there. And this idea of sending humans to Venus is a pretty good one, I think. Now, obviously, you don't want to go to the surface of Venus. That's death. It's hot enough to melt, I don't know, cotton candy down there, lead. What else could you melt on the surface of Venus? Anyway, I got to come up with a list of things that you can melt on the surface of Venus. Anyway, you don't go down to the surface of Venus. You stay in orbit. But it is relatively quick to get to Venus, just a couple of months. It is relatively quick to get home from Venus, just a couple of months. And so all of the things that you would be doing on your way to Mars, you would also be doing on your way to Venus. But if there's any problem, you could abort the flight. You could take a return trajectory to get yourself back to Earth. There are ways to rescue. It's just closer and more feasible. And so for a lot of the logistics issues, it makes a ton of sense to go to Venus. But if you're going to follow on that, like, it makes the most sense to go to the moon, fully explore the moon, spend a lot of time getting accustomed with that, go to an asteroid. They're a little farther, a little tougher to get to, practice there, go to Venus, practice, and then go to Mars. But, you know, there's a lot of people out there who they want their boots on Mars and they want it now. And no amount of doing a flyby of Venus is going to make them happy. Now, what's really cool, and I've said this many times, and I feel like I need to write this as a story or something, but like every good idea that has been proposed these days was originally thought of back in the 60s. There is a paper that proposes that there be a human flyby of Venus. This was suggested to be a follow-on to the Apollo missions, that you would have a couple of astronauts, they'd fly past Venus, take a bunch of pictures of the surface, fly back to Earth, and you would have just more practice and experience in flying farther away. You're going to deal with the radiation of deep space. You're going to deal with supplying material for the trip. You're going to find out how your toilet is going to behave. You're going to find out what kinds of food and water the astronauts are going to go through. What are the stressors? What are the kinds of technologies that are going to go wrong? So I'm a fan of the idea. You know, there have been other proposals, obviously, that you can go into the atmosphere of Venus. And so when you're in like around 75 kilometers altitude on Venus, the temperature of the atmosphere and the pressure are the same as Earth. And so you could stand outside in a short sleeve shirt with a breathing apparatus and you would be comfortable on Venus, apart from the sulfuric rain. But you might be above the sulfuric acid rain. So really, you just can't breathe the carbon dioxide. So I do like the idea, but I think that for a lot of people, it seems like a waste. You fly past Venus, or you orbit Venus for a little while, you take some pictures, and then you come home. That is not the same as setting foot on the surface of Mars, another planet, the second best place that we could go beyond Earth that feels the most like humanity's future second home. And it feels like you're just putting the idea off. But I think it's a great idea. I mean, I think go to the moon, get good at it. Go to an asteroid, get good at it. Go to Venus, get good at that. Then go to Mars. If you can wait. Are you patient? I am. Music cassette. What is the point of bringing humans down to the lunar surface? So whenever we talk about this idea of human beings flying in space in general, people will say, why? What is the point? And there is no reason. Like, there is no logical reason to send humans to space. I mean, yes, if you had an astronaut on the surface of the moon or an astronaut on the surface of Mars, they would be vastly more capable than a robotic mission in doing various kinds of science operations. But they are vastly more expensive. It's more dangerous. You got to keep them alive, etc., etc. While you could just fly a robot to do the specific kinds of science that you want. And if you have new scientific questions, you send another robot, you do more science. So there's no good reason to send humans to space. There's no argument that could be made for it being the rational best thing to do, that humans are the best for this job. But we still want to go. We still want to leave Earth and fly to space. And that's because that's what human beings do. We want to leave the comforts of where we are, and we want to explore, and we want to keep exploring forever. And we can't stop it. It's the way we feel. Like, why do people climb Mount Everest? Because it's there. Why do people want to go to the moon? Because it's there. Why do we want to go to Mars? Because it's there. Because our future is to become a spacefaring civilization, that we will eventually live across the entire solar system and eventually live across the Milky Way and live across the universe. And how do we get there? We get there by taking it one step at a time. And the first step is the moon. The moon is close. And so we go to the moon. And there's an argument to be made that it's too soon to go to the moon, that you wait. And it was definitely back in the 1960s and 70s when they first went to the moon. It was like a huge chunk of their gross domestic product. It was a lot of money. It's significantly less today. And if you waited 20 years, 50 years, 100 years, it would be significantly less then. But you have to go sometime. At some point between now and our solar system spanning civilization, we took the various steps and learned all the lessons one step at a time. And so the only reason to go to space is to go to space. The only reason to send humans to the moon is to send humans to the moon. Because how can you send humans to the moon if you haven't sent humans to the moon? See, it's a tautology. It's self-reinforcing here. And we go to explore. And so I think, like, whenever anyone tells you that there's some reason, like, we're going to go to the moon because we're going to get out and dig up helium-3, or we're going to go to the moon because then we can just, like, crunch rocks in our geology kit. We're going to go to Mars because, I don't know, we can find life there. Maybe, but robots can do that too. No, we go to these places because we want to go to these places. Stanman, since we've never spent any time at Lagrange points around Earth until just recently, and they purportedly have unique gravitational properties that we plan to make use of for parking instrument structures, how can we assume them as devoid of space meteorites as general space is? The Lagrange points, in case people have never heard about them here on my channel, which I know is impossible, are these places of gravitational interaction between two large bodies in the solar system. So the sun and the Earth is going to have 5 Lagrange points. The Earth and the moon will have 5 Lagrange points. The sun and Jupiter, the sun and Venus, etc., etc., etc. There are Lagrange points between large objects and small objects. And the way the Lagrange points work is that 3 of them are unstable. The 3 that line up. So the one on the other side of the sun, the one between the Earth and the sun, and the one on the other side of the Earth. Those are unstable. You can teeter at one of these Lagrange points and use very little fuel. But the moment you start to drift away from it, you are going to fall away and you're not going to be stuck in that Lagrange point. And then there are the stable Lagrange points. Those are the ones that are the L4 and the L5. They are 60 degrees ahead and 60 degrees behind the Earth in its orbit. And there are objects trapped in the Lagrange points. Not many, and they're not very big. And relatively speaking, for another object that is in that Lagrange area, they're not very dangerous because the various micrometeorites and stuff that's in that area are not moving very fast compared to you. So just like flying through the asteroid belt, like you have to go way out of your way to even find an asteroid. It's not like you're going through the asteroid belt in an episode of Star Wars. It's much sparser. And so, like, how do we know that, like, where James Webb is doesn't have any trapped objects? Because that's how gravity works. Like we couldn't have gotten James Webb to that place if we didn't understand how gravity worked. The same gravity that predicts that this balanced place exists also predicts that there won't be anything stuck in there because it is unstable. Nothing can remain there without a thruster on board. And so the only reason that James Webb can be where it is because it is about once a month firing its thrusters to maintain position. And the second it runs out of propellant, it'll drift away and the Lagrange point will be relatively empty again, although, be some other spacecraft that have flown there. But anyway, you get my point. Series K. Lee. Did those last pictures from DART look familiar? All right, this isn't a question about space, more of a comment, but I'm still going to tackle it because it gives me a chance to talk about the DART mission. And about 30 minutes before I went live with this episode, we saw NASA's DART mission crash into asteroid Dimorphos, which is the moon of asteroid Didymos. I guess people call it Diddy Moon. And it was incredible. It was what an amazing thing. And hopefully Chad will show off the video as I'm talking right now. But we saw over the course of an hour this tiny little dot. And then the dot got bigger and bigger and bigger. And it resolved into an asteroid and its moon. And it got bigger and bigger and bigger. And then Didymos flew past. And we got closer and closer and closer. And then the asteroid filled the screen. And then the feed went loss of signal, and that was it. And it was amazing. I mean, we've never seen one of these flybys, impact missions, covered in essentially real time. Like the time delay was about 45 seconds from when the spacecraft was sending this signal back home to Earth, and we were actually seeing it. And, series comment here is like, did it look familiar? Yeah, it sure looked familiar. Like when you look at the surface of asteroid Bennu from the OSIRIS-REx mission, and you look at the surface of Ryugu from the Hayabusa 2 mission, you're seeing something that looks really familiar, which is this rubble pile of rocks, boulders, jumbled together. It's going to be really interesting to see once the data is finally in, what did it hit? And how does that compare? Are we going to find that asteroids are very different from one another? Or are all the little asteroids out there going to be these jumbled up piles of debris that are collected together through mutual gravity? So take that, asteroid. Mr. Trudy is saying in the comments that DART avenged the dinosaurs. I like that. Dinosaurs, we did this one for you. And we will now know what it takes to shift an asteroid in its orbit, and we will be better prepared when a killer asteroid is on its way to Earth, and we'll know what it takes to shift an asteroid into a safer trajectory. So congratulations to everyone on the DART team. What an amazing mission to actually watch and see this happen in the final phase of this. And yeah, so great. Alberto DC, could Webb seek Oumuamua, maybe pictures? Unfortunately, Webb can't see Oumuamua. It's too dim even for Webb. So at the time I'm recording this video, the brightness of Oumuamua is about magnitude 37, which is incredibly faint. You can see magnitude 5 objects with the unaided eye. And then dimmer than that, you need a telescope. And most telescopes top out around magnitude 12, maybe 15. Webb can see magnitude 34, which is incredibly faint. It's a space telescope. It's one of the biggest telescopes I mean, it is the biggest telescope ever launched into space. And so it can see magnitude 34. But Oumuamua is still too faint for Webb even to be able to see. Now, that said, we know where Oumuamua is and where it's going. We know the trajectory. And so, in theory, we can still chase down Oumuamua if anyone was willing to do it. In probably the next 10 years or so, you could still launch a spacecraft with a, say, Falcon Heavy rocket or on an SLS on a intercept trajectory that could catch up with Oumuamua in the next 50 years or so. Land on the asteroid, take pictures, send images home, and give us more information about what Oumuamua is. You could even theoretically, with an even more advanced propulsion system, retrieve a sample of Oumuamua and bring it home, although you probably would be looking at like 100 years from now. And so instead of chasing down an object that is already on its way outside of the solar system, scientists are going to wait for the next one and they're going to pounce. And so we know that in 2028, they're going to launch a new spacecraft called the Comet Interceptor, the Interstellar Interceptor Mission. And this is going to be a spacecraft that's going to loiter at the Lagrange point. It's going to hang out with the European Space Agency's Ariel mission, which is launching in 2028. And this is a spacecraft that's going to be looking at the atmospheres of exoplanets. And it's going to wait for another interstellar object to pass through the solar system or a really long period comet. And then it's going to fire its rockets and it's going to intercept with that and take some pictures as it flies past. So do you build this gigantic spacecraft that's designed to chase down this object that we know is out there? Or do you wait with a much simpler spacecraft and wait for something that you know is going to, we've had Oumuamua, we've had Borisov, we've had interstellar objects before. There are likely thousands of them passing through the solar system right now. We just need to find the next one. And hopefully with something like, say, the Vera Rubin Observatory, which is going to be cataloging everything that moves in the solar system, we're going to find out another one of these interstellar objects. You're going to have the interceptor spacecraft ready to go, and you're going to get those images. Now, that's not going to solve the, what if Oumuamua is an alien spacecraft problem? But it's probably not an alien spacecraft. It's probably just a rock, and more rocks and balls of ice are on their way through the solar system all the time. More questions in a second, but first I'd like to thank our patrons: Chris Hill, Otnot, David Stillwell, David McClure, Jorge Amador, Pedro Garcia, Leopold Roos, Steve Martini, Herb Goodfellow, Jason Carlson, and the rest of our 1,055 patrons for their generous support. Want our videos with no ads? Join our community at patreon.com/universetoday, and I'll also remove all the ads from the Universe Today website for life. Douglas Federoff. Hey Fraser, if you could witness any astronomical event in history, past or future, what would you choose to see? There are a bunch, because there are incredibly extreme events that have happened in the past. They don't happen very often, but when they happen, they are like, you can't compare them to anything else. Obviously, it would be amazing to see a bright supernova go off relatively close by. Like if Betelgeuse went off, we would be able to see it in the daytime. But it's like a star. We've looked at the sun. We know what a star looks like. Yeah, sure, it would be bright. You'd be like, whoa, it's daytime, and yet there's that star. No, the thing that would be amazing would be that we know that comets have come so close in the past that they've passed through the upper atmosphere of the Earth. It doesn't happen very often, every few million years, but it does happen. And can you imagine looking up as this giant comet is flying right through the atmosphere, like at night, with its long tail glowing? It would be incredible. And that would be something that I would love to see. It would be terrifying because this thing that potentially could end life on Earth is passing through the atmosphere of your planet. But wow, that would be absolutely incredible to see. So that's the thing that I would love to be able to see. But then there's lots of other things out there that would be incredible. Really powerful auroras, like the Carrington event, when you could see auroras down at the equator of the Earth. Really powerful meteor storms like the one we saw in 1966, but I'm sure have happened even more so in the past. I'm sure there's times when there have been hundreds of thousands, millions of meteors an hour. It looks like the sky is truly falling. That would be incredible. But yeah, I think I'd like to see a comet pass through the atmosphere of the Earth. Samuel Garland. Hey, Fraser, what do you think is the most influential image of or from space? Well, I think that obviously images of some of the planets across the solar system. Like when you think about when Galileo was the first person to take his telescope and look at the moon, look at Jupiter, look at Saturn, and see these features that no human being had ever seen before. He looked at the Milky Way, saw that what seemed like clouds were actually stars. He saw craters on the moon. He saw the crescent of Venus. And suddenly these things that were just bright dots in the sky were revealed to be worlds all on their own. And that must have just been mind-blowing. So it's not an image, except in Galileo's brain, and yet it is so influential because it began this kind of inexorable path towards us realizing that we're not the center of the universe. Beyond that, in terms of photographs, I mean, you've got the first photographs from other worlds when you've got the flybys of the moon from the Soviet spacecraft. You've got flybys of Mars from NASA missions. You've got flybys of Venus. You've got the flybys of Jupiter and Saturn from the Pioneers and then the Voyagers. You got the images of Pluto. So all of those firsts, there's nothing compares to a spacecraft sending a picture. The pictures from the surface of Mars from the Viking spacecraft, pretty amazing stuff. But I would say like one of the most influential images has got to be some of those first images of planet Earth taken from space. That for the first time in human history, we could see the spherical shape of our own planet, see it hanging out in the cosmos as just this single dot of light. And of course, the famous words from Carl Sagan that everybody, lives on that planet. Everyone who's ever lived and died is right there. And I think it's hard not to get a sense of our own insignificance and also potential when you look at these pictures of planet Earth seen from space. And it's incredible to think that this stuff all came in within a human lifetime. I mean, there are people who are watching this video right now who were born before those first images were made available to human beings. And yet here we are today with satellites that are watching the Earth continuously, predicting our weather and so on. And astronauts in space who are looking out the window right now and seeing the curvature of the Earth and getting the overview effect and all that. So I would say the most influential image that we have is the picture of Earth. The one from Apollo, the blue marble image, I would say is probably the greatest image, in my opinion, ever taken. James L. Hey, Fraser, what would be the advantages and disadvantages of a Vera Rubin in space? Can you imagine? Like the Vera Rubin is an 8-meter telescope. It's essentially the same size telescope as the Very Large Telescope's individual 4 telescopes. But it has this incredibly wide field of view, and it works really fast. It will image the entire night sky over the course of 3 days, and it will be able to see supernova and asteroids and comets and Planet 9 and then weird things we didn't even know were out there. Like nothing else that's ever been produced to this point. And it's one of the telescopes, I've been going on and on and on about it for years now, and yet we are now just probably about a year away from seeing first light from this telescope. It's going to change everything. What if you put it in space? I mean, so the downside of Vera Rubin is that it's located in the southern hemisphere. And so it can only map the sky that is visible from its vantage point in the southern hemisphere. It won't see stuff that's happening in the northern hemisphere. In a perfect world, we would have a northern Vera Rubin observatory as well. And the two would be working in concert and the images would be stitched together. And we would have this all eyes on space. But can you envision a space-based Vera Rubin that is working its way through the entire cosmos every single night? maybe avoiding the sun. But apart from that, it is taking pictures of everything in space, night after night after night. You could probably get by a factor of 10 again in terms of sensitivity, in terms of catching things that are happening very quickly. Imagine if you got faster, like you were maybe taking images every few hours, every few minutes. So there's plenty of room to go. Now, the disadvantages are that it's crazy expensive. Like, you would need to launch this enormous telescope into space and have it be able to do this kind of function very quickly. But the other big issue is the data. The Vera Rubin Observatory is going to be producing an outrageous amount of data. More data than would fit on anyone who's watching's hard drives by a factor of thousands. It's just too much data. And so as soon as you send this thing off to space, you're going to have to try and get this data from space back to Earth. Well, here on Earth, you just got fiber optic cables, enormous server arrays, the internet, and you can scale it up. But once you've got this thing out in space, you're having to send your data back in this tiny little straw of bandwidth. And you would have to figure out ways to compress and manage all that data on the telescope and then send interesting things back home, and you wouldn't be able to get the same kind of fidelity. I don't know, maybe you could like send a bunch of hard drives back home and they would fly through the atmosphere. I don't know. We need better communications technology for that to really work. So for now, we don't have the technology to handle the data that a telescope like Vera Rubin would be doing from space. We need more infrastructure, bigger radio dishes, a much more capable deep space network. Lasers. That's the answer. Lasers. Yeah, a whole bunch of lasers just pointing back at Earth, sending data nonstop. Be cool. Love, peace, and respect. Why don't they use the sun for a gravity assist for faster speed? On the one hand, you can't really use the sun as a gravity assist because you are already in orbit around the sun. So when you think about how a gravity assist works, like say you want to fly past Jupiter and you want to use the gravity of Jupiter to pull you forward. So what you do is you fly towards Jupiter, and as you're getting closer and closer to Jupiter, Jupiter's gravity pulls you in and pulls you up to its orbital speed around the sun, which is actually slower than you were going. But the point is you gain orbital momentum. It's essentially reaching down a hand and it's pulling you up to its level. And then you fly past Jupiter and now you've got additional velocity that allows you to go a lot faster. You also slightly slow down Jupiter, but not enough that anyone can notice. But you know, if you're going to try to gain the orbit of the sun, it wouldn't really work. Now, if we wanted to go to another star system, say there was a black hole out there or something, we could do a flyby of that black hole and we could get a gravity assist of some other star system, but because they're already in orbit around the sun. Now, that said, there is a very specific maneuver, and I'm sure a lot of the people who are watching this video are like screaming in their mind, like the Oberth maneuver. So there is this orbit that you can take where you fall towards a heavy object like the sun and you fire your thrusters, and just as you just miss it, you reach kind of your maximum velocity, and then you have this multiplier that accelerates you farther out into the solar system. And you can totally use that as a gravity assist. It's just like a gravity assist in a different way. And this idea has been proposed. That I did an interview with Les Johnson talking about solar sails, that solar sails work the best when they are really close to the star. And so you could fly really close to the sun, fire some like ion engine or something that takes you really, really close. And then just as you reach the closest point of the sun, engage the solar sail, your maximum amount of radiation falling on your solar sail, and then you use that to slingshot yourself out. And we talked earlier on in this episode about being able to maybe chase down Oumuamua. And if you were willing to use this technique, you could actually get to Oumuamua quicker. And so after a while, pretty much the only way that we could reach Oumuamua is to use this Oberth effect to be able to fly past the sun and get out there. So there are definitely some options on how you could use a heavy object like the sun to speed up your flight. Griffin, is it possible that Planet 9 hasn't been found because the sun is blocking our view of it? No. Like if there was a planet on the other side of the sun, it would absolutely be blocked from our perspective by the sun, but it would have to be on the same orbit as the Earth, essentially in the Lagrange point, the L3 Lagrange point, the one that's on the other side of the sun. And an object could absolutely be there, but only if it has thrusters to maintain itself and perch at that position at the L3 point. The second it runs out of propellant, it starts to drift away from the L3 point and it becomes visible. And over time, you see it more and more, and eventually it crashes into the Earth. It's not stable. And so if you had another planet, Earth, something on the other side of the sun, we would crash. Now, once you get farther away, then when you think about the way the planets work, right? Earth takes 1 year to go around the sun. Mars takes 2 years to go around the sun. Jupiter takes 12 years to go around the sun. And so Earth goes around 12 times for every time that Jupiter goes around. And so, yeah, there's definitely times when Jupiter's on the other side of the sun, but only for a month or two every year, and then it pops out the other side of the sun from our perspective. And the same thing would happen with Planet 9. If Planet 9 is on the plane of the ecliptic like the Earth, then yeah, for 1 or 2 months every year, Planet 9 is hidden behind the sun, but for the other 10 months, we could see it. And we don't see it. Greg Me, where are we as a spacefaring race in 50 years? I'm currently a 45-year-old space guy. What will I be seeing around my last years? I'm a little older than you, but sure, what will we see? I mean, I don't know about you. I was there for the launch of the space shuttle in 1981. Not there, but, I was watching my television and lived through the Viking missions, the Voyager missions, the Magellan mission to Venus, the flybys of Saturn. I mean, my professional career began just before the year 2000. I saw the construction of the International Space Station, the development of SpaceX, the missions to Pluto, Cassini, the Mars rovers, Curiosity, Perseverance. What does the future hold? Unfortunately, the really interesting places are really far. And so when you think about missions to Neptune, Uranus, like just to get a spacecraft out there, you're looking on the order of a decade to get like a good mission out there, not a quick flyby. Plus construction time, design time, you're looking at 20 years. Like if someone said, let's send a mission to Neptune, it would take about 20 years before we started to see those first images coming back home. But I do think that in the near term, we're going to see a permanent presence on the moon. And I would say by 50 years, we will have a permanent presence on Mars. We'll have a permanent presence on the moon, a permanent presence on Mars, and a permanent presence on an asteroid or two by the time we die. And obviously, 200 years from now or 100 years from now, humanity will be all the way across the solar system everywhere, in every nook and cranny. And we will have a very robust solar system infrastructure. It's just that it's a compounding interest thing. So we're here right at the very beginning of this process. I know for a lot of people who watched the Apollo missions 50 years ago felt like you were right there at the beginning. That was a false start. Now it's the beginning. And now we're there. We're going to be going back to stay. So I think it's going to feel fairly similar. There's going to be a bigger version of the space telescopes. There's going to be more exploration of the various places in the solar system. There's going to be a permanent moon base, probably a permanent Mars base, but not that kind of really thrilling space future, science fiction future like The Expanse, where people are everywhere. Give it another few decades, 100 years after that. Bravo 01. What would happen if you suddenly remove the black hole at the center of the galaxy? Does it really hold the galaxy together? Nothing would happen. A black hole, supermassive black hole, even though it can be millions or even billions of times the mass of the sun, is a fraction of the mass of the galaxy. It's about 1%. So if you take all the mass of the entire Milky Way and you take the supermassive black hole and you pluck it away, then the mass of the Milky Way is now 99% of the mass of the Milky Way. And nothing really changes, except for stuff that was in the environment around the black hole. You've got these stars that are orbiting like comets around the black hole. They fling off into deep space, but the rest of the galaxy doesn't even notice. People always think of these supermassive black holes as the anchor, that they're the the center of the galaxy, but really they're just the densest spot, the place where a black hole sunk down to at the very middle. The thing that really holds the galaxy together is the dark matter halo. What we see as this visible galaxy, this spiral galaxy, is actually just this tiny portion of this much larger blob of dark matter that is rotating in space, and the galaxy's inside rotating with it. So no, if you remove the black hole, nothing would change. And that 1%, that's just the visible matter. Like, that's not even the dark matter halo, which is more, several times more than the mass of the Milky Way itself. So no problem. All right. Those were all the questions that we had this week. Thank you, everyone who asked them in the YouTube comments and everybody who joined me for the live show. Super fun. Remember, we do this every Monday at 5 p.m. Pacific time, and there should be a link to the next event just somewhere here on my YouTube page. So definitely click the notification bell and you'll be reminded when we do this next time. All right. We'll see you next week. You can get even more space news in my weekly email newsletter. I send it out every Friday to more than 55,000 people. I write every word. There are no ads and it's absolutely free. Subscribe at universetoday.com/newsletter. You can also subscribe to the Universe Today podcast. There you can find an audio version of all our news, interviews, and Q&As, as well as exclusive content. Subscribe at universetoday.com/podcast or search for Universe Today on Apple Podcasts, Spotify, or wherever you get your podcasts. A huge thanks to everyone who supports us on Patreon and helps us stay independent. Thanks to all the interplanetary researchers, the interstellar adventurers, and the galaxy wanderers. And a special thanks to Josh Schultz and Andrew M. Gross who support us at the Master of the Universe level. All your support means the universe to us. Thanks to all the moderators, and a special thanks, as always, to Chad Weber, Nancy Graziano, and Anton Poznikov.